Hello everyone, welcome back to Organic Chemistry 2 Lab. The experiment today will focus on the formation and reduction of an imine. Alright, it is spelled with an I, but you pronounce it as an E, so imine, right? So here we go, imine. So this imine looking word is pronounced E-mean, right? You so mean. E is mean. E mean. All right. So sorry, I'm channeling my children a lot. All right. So anyway, with that, looking at an imine formation, you're going to see this reaction take place between an aldehyde and a primary amine. And so our aldehyde here is going to be cinnamaldehyde, and our primary amine is going to be M-nitroaniline. Okay, and so we are going to see under acidic conditions the formation of our imine, and then we're going to reduce it back down to an amine with an A using sodium borohydride. All right. So a couple of things to kind of keep in mind here, right? We can consider this a condensation reaction because we do see, specifically if you look over the arrows right here, water leaves when you add these two together, you do see water leaving or being evolved as a product. Okay, now one of the biggest problems is we're going to reduce this imine, and so you really have two products here, the imine and then water. Why do I care? Why am I bringing that up? Well, with this water in particular, we do have a safety issue of concern when we reduce our imine using sodium borohydride, and I'll talk about that in a second. Now, other reductions, you can use something like Raney nickel or palladium or platinum. Use one of those transition metals to help you reduce the imine, the carbon-nitrogen double bond specifically. And you notice here that you don't see the Raney nickel reducing your benzene ring. All right, good stuff. Good stuff. Okay, now in terms of what's going on here, all right, I kind of wanted to actually go over the mechanism a little bit better. Now, when we look at our mechanism here for our aldehyde, which is going to act like an electrophile, and our primary amine, which is going to act like a nucleophile, we're going to see the lone pair on the nitrogen attack the partial positive carbonyl carbon. All right, and that's a good attack because then the pi bond with the oxygen can move up. All right, and that's why we see when that pi bond moves up, that oxygen becomes negatively charged. We have now 4 bonds on nitrogen, so that's why we see it having a plus charge. And so having this negative plus charge scenario going on, the negative charge, the lone pair on one of the lone pair on the oxygen can now attack one of the hydrogens that's bonded with nitrogen here and actually help satisfy these charges. All right, so we'll break the nitrogen-hydrogen bond, put a lone pair on the nitrogen, so it's no longer with a charge, and now the oxygen also no longer has a charge. All right, now at this point, this is kind of where we're stuck. Nothing can really happen without the use of some type of acid catalyst. All right, so using that acid catalyst, we can we can then see the oxygen of our alcohol group. The lone pair is going to attack one of those hydrogens, and we're going to see the formation of water from our catalyst. Okay, not actually water from the aldehyde and amine yet. Alright, so anyway, so once that happens, we've now turned that alcohol into water, which is a superb leaving group. Alright, it is splendiferous. And so we can see that water leave, and having that a lone pair on the nitrogen now, we can help satisfy the positive charge that would be on this carbon by having the lone pair form a double bond there. Okay, now, so at this point, what we would see, we have our nitrogen has a positive charge now, and this is where that catalyst part, the acid part of it being, the catalyst part of our acid being regenerated. So the water that formed from that can now come back take a hydrogen off that nitrogen and give it a lone pair. So now we have our imine, spelled with an I. We have our imine product formed here. And we've regenerated our acid catalyst. Okay. All right. Now, one of the things to pay attention to here, I told you that, water is one of the products that we have with this reaction, right? So if you just look overall like this, right, our reaction looks like this. You have your aldehyde, you have your amine, then you have your imine, imine, and then you have water as a byproduct. This water product is bad for the reducing agent we're going to use. We're going to be using sodium borohydride as a reducing agent. And so sodium borohydride can react with water to form the sodium boron species, which we don't care as much about. That's not the scary part. The bad part here is the hydrogen gas, H2, which is a flammable gas. And this reaction is spontaneous. It is favored. It has a delta H less than 0, so it's a negative delta H, right? We consider that a spontaneous reaction. So if we don't somehow remove that water, we're going to make a whole bunch of flammable gas. We don't want to do it. All right, it's not a pretty picture. We don't like doing it. All right, so with that in mind, some things that we can think about here. We can remove that water. In particular, if we think about azeotropes. All right, so azeotropes are not heavily focused on or explained, but one of the good thing about azeotropes is that you can have two components, say two solvents, if they can interact with each other in a way that they can reduce the boiling point of one or both of the components. So it's kind of like, think of somehow these two interact with each other, maybe not a reaction, but they interact with each other, and what winds up happening, they alter the physical properties of each component. And in doing so, they say, okay, well, cyclohexane here, I had a boiling point of A, but now through the interaction with water, I'm going to have a boiling point of now B. And so vice versa, when we talk about needing to remove this water, we do know that when we form an azeotrope of water with cyclohexane, we will see this boil off at 69 degrees C, which is much lower than the boiling point of pure water, 100 degrees C, right? So we've lowered that a lot. And so that's why the use of a distillation apparatus here, right? What you're actually going to do is you're going to collect this azeotrope over here so that you can keep making the imine and remove the water as it's being produced. Now, why is this good? Not just from the sodium borohydride standpoint, right? We are going to reduce our risk, right? We are going to reduce our flammable product risk, right? We're going to definitely lower how much hydrogen gas we'll produce in this reaction. But what's another important aspect of this? Well, let's go back and look at the generic reaction I gave you. You notice all those equilibrium arrows? What? So all these equilibrium arrows, if we are distilling off our water azeotrope, right? Well, water specifically. If it's forming azeotropes and if it's being distilled off, right, that means that at equilibrium, we're removing one of the products. So thanks to good old Le Chatelier, I'm not French, so I may have misspelled his name, but you can recognize Le Chatelier in there, right? Le Chatelier's principle tells us that if we reduce the concentration of one of our products, then we can thereby see that the reaction will push forward, right, and make more product, right, to compensate for that loss in equilibrium. Okay, so it wants to maintain that equilibrium, and it can't if we're constantly removing water. All right, so with that being said, we're pretty good with that. Now, one other side note here. All right, it's very important that you do this reaction sequentially, right? You're going to first make the imine, right? Then you're going to reduce it, not using Raney nickel, but using sodium borohydride. All right, and don't think this is the product you make, because this, right, is not the imine that forms between these two. All right. You need to pay attention to the structures. Okay. One of the things to pay attention to is you do not want to add sodium borohydride straight away, because one, you do have to worry about hydrogen being produced as water is formed in the imine reaction, imine formation reaction. But another thing is sodium borohydride is a reducing agent you should have seen before that could reduce aldehydes and ketones, right? So it reduces an aldehyde to an alcohol. Not good if you're trying to do this imine formation, right? So if you're trying to do that, what does that mean? That means the first step of the reaction, right? The first step of your reaction, you have to have the lone pair of the nitrogen interact with the carbonyl carbon. You can't do that if you're turning this guy into an alcohol, right? This reaction won't happen if that's an alcohol. So we don't want the sodium borohydride in there turning it into an alcohol. All right. Anyway, with that, you should be prepared to work on your pre-lab quiz. Good luck.